This is the second part of the 4-2 lecture. And in this lecture, we're going to be talking about some good experimental design techniques, and we're going to be talking about some additional design periods of experiments. Um, the logic of the randomized comparative experiment basically saying it's like, hey, I got two similar groups, and they're similar as similar as can be, except for the actual treatment. But the question is, how do we make it so that even the treatments feel almost the same? And that is, sometimes we use a placebo, which is a dummy treatment, and we do this to defeat something called the placebo effect. And the placebo effect is an idea that sometimes people react to even a dummy treatment because of other things. For example, imagine someone who they're testing a diet pill, and some people get the pill, and the other people don't get the pill. Well, the act of getting a pill that even though it doesn't have an active agreement, may make people think about living more healthy lives or eating better or other things like that. And that can lead to a placebo effect. Whenever possible, we should have a placebo. And also, the subject should be double blind. In a double blind experiment, neither the subjects nor those who interact with them and measure the response know what treatment is being given. So everyone's in the dark about what group they're in until you actually see the final results. But in a single blind experiment, only the subjects are unaware what treatment they're getting. Um, let's take this idea and see if we can make some sense out of it. In an interesting experiment, researchers examined the effect of ultrasounds on birth weight. Pregnant women participating in the study were randomly assigned to one of two groups. The first group of women received an ultrasound. The second group did not. When the subjects' babies were born, their birth weights were recorded. The women who received ultrasounds had heavier babies. Did this experiment take the placebo effect into account? And the answer is um, the placebo effect was not taken into effect as there was no, and I'll use the word dummy treatment. There was simply no other treatment. They just simply didn't get the ultrasound. Why is this important? Um, you can think of some mothers, not possessive mothers, some mothers may respond, meaning they have some reaction to the attention. Or there may be something else that they're responding to that the people who did not get the ultrasound didn't get. And it may have nothing to do with the ultrasound. Okay. Thus causing um, a placebo effect. The ultrasound really didn't do anything, but the mothers reacted anyway. Okay. Was the experiment double blind? And the answer to that was the experiment was not double blind. See how I answered the question right away? And then let's say the reason. Because the mothers knew whether they were getting an ultrasound. Why is this important? Again, the reaction to getting any treatment may affect um, birth weights. So we don't know whether the ultrasound is doing it or just any attention that we might be giving. So based on the answers to one and two, can you describe an improved experiment? And I think they mean, can you incorporate both a placebo and double blind? And the answer is um, uh, have a placebo group where subjects get a fake ultrasound. So it's an ultrasound in that they're going into a room. Um, the ultrasound machine is there. It's applied to uh, the mothers, but that is um, the ultrasound machine is not turned on. Now, for that to happen, you can get um, the the subjects certainly are single blind, but the person giving the fake ultrasound, but but you probably can't pull off a double blind. As the person who's applying the fake ultrasound would have to know which treatment group um, get in there. Um, by the way, make sure uh, ultrasound is um, the screen is not visible. That would kind of break the illusion. Okay. All right. So that's how we might make an experiment a little bit better. In truth be told, some experiments simply cannot be done in a double blind fashion. All right. Now let's change the subject a little bit and let's talk about one of the big reasons why we're doing all of this work, and that is to move towards, again, inference. Now, what is inference? We do an experiment and we see difference in responses. Okay. And we want those differences in responses to be so large that they're unlikely to happen by chance variation. It's not that, oh, on this one-time experiment, we saw this little bit of difference, and that little bit of difference is something that could have happened by chance. Think about flipping a coin 100 times and getting 51 heads. Is it exactly what you expected? No, but it's not so outrageously different that you can't think of it not happening by chance. Um, but when we're done, we'd like to be able to apply our findings to a larger group. And that's where we again talk about the idea of inference, sampling, coming to a conclusion, inferring onto a large population. We don't think we can infer onto that large population unless we think the outcome is statistically significant. That is, that the observed effect is so large that it would rarely happen by chance. And we say that a statistically significant association in data from a well-designed experiment does imply causation. we get to the point where we can actually say this thing did cause that other thing. And we call this whole situation statistically significant, which means in class, if we use the word significant, we better be doing it in the context of this particular idea. Experiments, well designed, and an outcome so large that it didn't happen by chance. Now, in the class notes, we go to this activity that tries to get at the idea of significance. We're going to do this particular activity in class with everyone so we can all get that, go through that procedure and see that out.